Hello, welcome to Chemistry Chapter 15, Final Exam Review. You will need the worksheet and a calculator, and that ought to be good enough. So let's start with number one. We have this reaction. It says the equilibrium concentrations for the above reaction are 1.5 molar for HCl, 1 molar for MgOH2, 2.5 molars for MgCl2. What's the equilibrium constant for this reaction? Is the equilibrium weighted towards the products, reactants, or neither? Okay, so I've gone ahead and written out the reaction here. So we need to calculate big K. And in the numerator, you have the concentrations of the products raised to the power of the coefficient. So the only product that you will use, because you only use gases and aqueous substances, no liquids, so we don't include water. That's to the first power. You wouldn't have to put that, but I'll put it for illustrative purposes. And then in the denominator, we would have 1.5 molar for HCl. We need to square that times 1 molar for magnesium hydroxide. All right, so in your calculator, I'm just going to kind of ignore that 1 molar since it's just 1, and I would have 2.5 divided by 1.5 squared. That is 1.11. The unit is going to be molar on top and then molars cubed on the bottom. So that's going to be 1.11. That'll cancel out and this will go to squared. So 1 over molar squared. Remember, the unit's a little more important than normal. So it is slightly weighted towards the products because it's greater than 1. But just very slightly. So you could also use a right arrow there to show it's weighted towards the products. Okay, so number 2 says concentrations for the following reaction, 2A plus 3B yields 2C plus 2D, are measured as follows, and it gives the numbers. The equilibrium constant for this reaction is 3.5 molar squared. Is the reaction at equilibrium, and if not, which way will it shift to achieve equilibrium? All right, so let's write out this reaction. We have 2A, which is a gas, plus 3B, which is a solid, yields 2C, which is aqueous, plus 2D. So also aqueous. So I'm going to put underneath, so the concentration for A is 1.2 molar. For B, it's a solid, so we're not worried about that. For C, 0.8. And again, the brackets mean concentration. And then for D, 1.6. So let's calculate K at this point in time. It's going to be 0.8 on top. And then we're going to raise that to the stoichiometric coefficient power, so 2, times 1.6 molar, so that's D, also squared, divided by 1.2 molar, and that's going to be squared. Okay, because of the 2 out front. All right, so we've got 0.8 squared times 1.6 squared. I like to hit enter. Then we're going to divide that number by 1.2 squared. That's 1.14. and it would be molars to the fourth, because you add those exponents, divided by molars squared on bottom. So that's 1.14, and the unit would reduce down to molars to the fourth over molar squared would be molar squared. Now, is that at equilibrium? Well, the problem says the equilibrium constant is 3.5. So it's not at equilibrium yet. It needs to get bigger. Well, in order to get bigger, we need to increase the numerator. The numerator is the products. So it must shift toward the products. And if you prefer, you can just do an arrow towards the products. All right, so there you go. Let's look at number 3. So number 3 says, give the expression for the equilibrium constant for the following reaction. We don't have any numbers here, so our expression will just simply be with our compounds. So our reaction is NH4Cl, which is a solid. And that's NH3 gas plus HCl gas. Okay, we don't include the solid in the calculation. So we'd have the concentration of NH3, and it's to the first power, times the concentration of HCl, also to the first power. And then you don't have anything, because it's a solid, in the denominator. So you can just put it over 1, or you don't have to put it over 1. You can just have concentration of NH3 times the concentration of HCl. All right, let me clear the board and we'll start talking about Le Chatelier's principle. Okay, so number 4. So we've got 3 problems in a row like this. We have NaCl aqueous. So if you want to follow along, plus H2O liquid, plus CO2 gas, yields NaHCO3 plus HCl. Okay, so part A says, what will happen to the concentration of CO2 if HCl is removed? So I'm going to put a question mark. What will happen to CO2? HCl is removed, so I'm going to put a down arrow. We're reducing the amount of HCl. Okay? Well, we would have, if we reduce the concentration of HCl, we're going to have fewer collisions on the product side. That means the reactant side will have more collisions. That means the reactant side will win. Okay, so the winner gets the arrow. All right, and then it's going to, the reaction is going to try to shift to bring more collisions over on the right side. So since the arrow is pointing to the right, it will drain the left side. So what will happen to CO2 is that the concentration will decrease. Okay, let's look at B. It says, what will happen to the amount of H2O if the concentration of NaCl is increased? All right, so the amount of H2O, I'm going to put a question mark here. We're going to increase NaCl. That means we would have more collisions on the left. the left side would win. The winner owns the arrow, so it's going to point it towards the other side. So what would happen if the arrow is filling the products but draining the reactants because it's pointed to the right? H2O, then the amount would decrease. All right, we are stressing the equilibrium with an aqueous substance, so even though H2O is a liquid, we can increase or decrease it by stretching with a gas, by stressing the reaction with a gas or an aqueous substance. All right, part C says what will happen to the concentration of CO2 if more H2O is added. Okay, let's put a question mark. What will happen to CO2 if H2O is added? Well, you can't stress an equilibrium with a liquid or a solid, so nothing will happen. Nothing happens to CO2 in that case. All right, part D says what will happen to the concentration of HCl if more NaHCO3 is added. Okay, so we're adding NaHCO3. We want to know what is the change in concentration of HCl. Okay, so if we have more collisions, we're increasing the concentration of NaHCO3. Therefore, we have more collisions on the right side. Therefore, the right side will own the arrow. In order to achieve equilibrium, it will drain the right side and fill the left side. So, if the arrow is pointed to the left, the right side is being drained, it will decrease. So 3 out of the 4 of these scenarios are decrease, and then 1 was nothing. Okay, I think number 5 only has 2 parts, so I'm going to try to fit it on the bottom part of the board here. So we have 2ClO gas, and we are decomposing that into Cl2 gas plus O2 gas. And it says that we have negative 100 kilojoules for delta H. That means it's a product. If it's negative, it's exothermic. The energy is a product, so I'm going to put it on the right side, 100 kilojoules. All right, the negative just tells us which side it goes on. All right, part A says, what will happen to the concentration of ClO if the temperature is reduced? Okay, so question mark here. The temp, I'm going to write that over here to the right, temperature is reduced. Well, when the temperature is reduced, the reaction shifts towards the side with the energy. If it's reduced, towards the side with the energy. So the reaction will shift to the right. That means it'll fill the right, drain the left. Okay, so what will happen to ClO is that it will decrease. All right, part B says, what will happen to the concentration of O2 if the temperature is raised? Okay, so the temperature is raised. We want to know what will happen to O2, so let's put a question mark there. If the temperature is raised, the reaction will shift away from the side with the energy. So that would be away from the products towards the reactants. So the products are drained, the reactants are filled. So if the products are drained, O2 will decrease. All right, a lot of decreases for these scenarios so far. All right, let me clear the board. We'll move on to number 6. Okay, our reaction number 6 is 3TiO2. That is a solid. Plus 4C, solid. Plus 6Cl2, which is going to be a gas. And then we have 3TiCl4, titanium tetrachloride, which is a gas, plus 2CO2, plus 2CO. Okay, so we've got 4 parts to this. So part A says, what will happen to the amount of TiO2 if the pressure is raised? Now, when we're dealing with pressure, we need to add up the number of gas moles on each side. All right, it's all about the gas moles. So on the left side, we have 6 gas moles. And on the right side, we have 1, 2, 3, 4, 5, 6, 7 gas moles. Okay, so part A says what will happen to the amount of TiO2 if the pressure is raised. Well, if the pressure is raised, the reaction will shift towards the side with the least gas moles. The most gas moles will win. So it's going to shift to the left, away from the most gas moles, 7 versus 6. So it will fill the reactant side. And since TiO2 is a reactant, it will increase. All right, part B says, what will happen to the concentration of Cl2 if the pressure is decreased? Well, if the pressure is decreased, the arrow will just simply go the other direction. So if you got part A right, you should get part B right. We're wanting to know what will happen to the concentration of Cl2. Well, Cl2 is a reactant. The reactants will be drained. The products will be filled, so it will decrease. All right, part C. Pressure is decreased in part C, so the arrow, just like in part B, will be going to the right, towards the side with the most gas moles. We want to know what will happen to the concentration of CO. It's way over here to the right. CO is a product. The products are being filled because the reaction is shifting towards the products, so it will increase. And then D, what will happen to the amount of TiCl4 if the pressure is raised? So if the pressure is raised, the reaction will shift away from the side with the most gas moles. Reactants will be filled, products will be drained, so it will decrease. All right, so there you go on this one. So it's increase, decrease, increase, and decrease. Okay, let's see if we can fit number 7 on here. Number 7 says, we've got two questions. What's the acid ionization equation for HBr and for H2CO3? Well, acids want to split into their constituent ions. Okay, so we have HBr. We're going to assume that's aqueous. That's going to split into H plus Br minus. Now bromine is in column 7, so it has a negative charge. It's already balanced there, so K, you're just going to use the equation for big K. It's going to be the concentration of H plus. Now don't forget the pluses and minus there, times Br minus, divided by the concentration of HBr. So not a base, so we don't add liquid water or anything like that. All right, part B, we have H2CO3. Now we have to get the equation, the chemical equation first, and then the equation for the acid, and that'd be K sub A, by the way. All right, it's going to split into H plus. Now there's a couple of different options because this has reaction steps. I'm going to do H plus and then HCO3 minus. If you did H plus CO3 2 minus, that would also be correct. Okay, but this is happening as well. And this is already balanced, so I'm not having to deal with if we did H plus and CO3 2 minus, then we'd have to put a 2 in front of the H here. So K sub A is equal to the concentration of H plus times the concentration of HCO3 minus over the concentration of H2CO3. All right. Let me clear the board here and we'll move on. It won't take very long for us to finish this up. If you hear a rattling, that's my music stand that's holding my papers. I need to work on that. Sorry about that. All right, number 8. Says, what is the base ionization constant equation for C2H7N? All right, the base ionization constant equation C2H7N, and that's aqueous. So for a covalent base, a non-hydroxide base, what you do is you add liquid water to it. So the water doesn't become part of the equation, but we need liquid water. A base wants to gain a hydrogen. So we'll gain C2H8N. But since it gained a hydrogen, we now have a plus charge. Plus 1. Plus OH minus. So the C2H7N nabbed a hydrogen, leaving hydroxide. So K sub B, right, is equal to the concentration of C2H8N plus times the concentration of hydroxide, OH minus, over the concentration of C2H7N. All right, and remember, if it's a hydroxide base, you don't need the liquid water. It will just split into its constituent ions. But we have, you can look at the extra practice problems from Chapter 15 if you want, or even the extra practice problems from Chapter 15 if you want to see an example like that. Okay, number 9. What is the pH range for acids? And as the pH gets smaller, does the acid get stronger or weaker? All right, it would be 0 to 6.9 or 6.99. However, I would accept 0 to 6.9. And as the pH gets smaller, the acid gets stronger. Okay, number 10. Which has the largest K sub A? A pH of 1 or a pH of 6.5. Well, a larger K sub A means a stronger acid, and a stronger acid would be the pH of 1.0. So stronger acid means larger K sub A. All right, number 11, what is the pH range for bases? And as the pH gets larger, does the base get stronger or weaker? pH range for bases will go from 7.1 to 14. Technically, if you want to put 7.01 to 14, that would be fine. As the pH gets larger, the the base gets stronger. Ionizes better. That's another way of saying that. What is the smallest case of B? pH of 7.5 or pH of 11.5? Well, the smaller the case of B, the weaker the base. So that would be a pH of 7.5. So weaker base means a smaller case of B and a lower pH. All right, that does it for the final exam review for Chapter 15. If you understood this, you're in great shape. Maybe you want to rework some of those suggested problems, maybe rework the extra practice problem worksheet or some of those from the book. And I will talk to you on the next one.